Along the Atlantic seaboard of occupied France, the German Kriegsmarine erected structures of concrete ambition that defied imagination. These colossal U-boat pens were not mere shelters, but engineering marvels designed to withstand the fury of Allied aerial bombardment. The Battle of the Atlantic was the longest and arguably most crucial campaign of the Second World War, a relentless struggle for control of the sea lanes. The success of the German U-boats posed an existential threat to Britain, whose lifeline depended entirely upon transatlantic convoys. As the war progressed and Allied air power grew, the U-boats became increasingly vulnerable while transiting to and from their patrols. The only way to protect them from the relentless RAF and USAF attacks was to build a protective shield that no conventional weapon could penetrate. Hitler himself decreed that these submarine bases must be rendered absolutely immune to attack, demanding an unprecedented level of fortification. Construction began on a series of massive bomb-proof bunkers in key ports like Brest, Lorient, Saint-Nazaire, and La Rochelle. These vast coastal complexes transformed quiet French harbors into bristling fortresses of concrete, steel, and flak guns. The scale of the construction was staggering, consuming immense quantities of steel, cement, and manpower from across the Reich and occupied territories. The pens were strategic prizes, guaranteeing the U-boats could rearm, refuel, and repair in safety, thereby keeping the pressure on Allied shipping. German engineers calculated the required roof thickness based on the largest bombs the Allies were known to possess at the time of construction. They believed the resulting layers of reinforced concrete, reaching several meters in thickness, created an impenetrable barrier. This concrete shield represented a technological declaration of immunity, a firm German conviction that their critical submarine fleet could never be harmed while in harbor. The structures stood as symbols of Nazi resilience and the seemingly insurmountable challenge facing the Allied air forces in their efforts to close the Atlantic Gap. The pens became a massive drain on Allied resources as Bomber Command was forced to repeatedly attack them with diminishing and often negligible effect. The initial frustration felt by Allied strategists grew into a deep, abiding urgency to find a solution to this concrete stalemate. They knew that until these bases were neutralized, the U-boat menace would continue to haunt the shipping lanes and prolong the global conflict. The very existence of these coastal behemoths challenged the fundamental principles of air superiority the Allies sought to establish. The concrete pens essentially moved the critical maintenance and resupply phases of the U-boat war into a safe zone. This forced the Allies to fight the U-boats only in the open ocean, which was a far more costly and challenging endeavor than striking them at their vulnerable moorings. The structures were a masterpiece of defensive engineering, but their very defiance would ultimately inspire an even greater innovation in offensive weaponry. The sheer dimensions of the U-boat pens were a testament to the industrial might and strategic paranoia of the Third Reich. The bases were essentially fortified, roofed docks capable of accommodating dozens of U-boats simultaneously for maintenance and resupply. At locations like the Karaman submarine base in Lorient, the structures were so large they formed their own industrial ecosystem within the heavily protected perimeter. The roofs were the most critical element, designed as layered defenses to dissipate the energy of impact and explosion. Early bunker roofs began at a thickness of around 4 meters, a depth considered utterly impervious to Allied ordnance in the early 1940s. However, As Allied bombs grew in size and payload, the Germans continuously upgraded the protection, sometimes adding subsequent layers of concrete on top of the original roof. In some cases, the final, finished roofs reached an astonishing thickness of 7 to 8 meters of solid, heavily reinforced concrete. This immense weight and bulk were achieved through the use of millions of tons of sand, gravel, and cement, all mixed and poured on site under high pressure construction schedules. The concrete used was a specialized high-density mix, specifically formulated to resist the shockwaves and penetration of even the heaviest conventional bombs. Inside the pens, the atmosphere was dark, damp, and intensely industrial, filled with the sounds of machinery, welding torches, and U-boat crews at work. The U-boats would enter through massive, steel-reinforced gates, which were often retracted beneath the waterline for additional protection. Once inside, they were completely invisible to Allied reconnaissance and immune to direct attack from the air. The strategic value was in the guaranteed turnaround time. A U-boat could return from a patrol, undergo repairs, take on fresh torpedoes, and be ready to sail again in a fraction of the time it would take without this protected infrastructure. Allied bombing raids that targeted the bases often looked like direct hits from the air, but were rendered completely harmless by the massive roof structures. Analysis of post-raid photographs consistently showed only superficial scorch marks or slight depressions on the concrete surface. The Germans, confident in their engineering, even placed anti-aircraft batteries directly on top of the bomb-proof roofs, using the invulnerability to their advantage. This tactical deployment of flak guns made the approach to the U-boat pens one of the most heavily defended pieces of airspace in all of Europe. The concrete defenses were more than just passive protection. They were an active part of the psychological warfare against the Allied airmen. Every failed raid underscored the German belief that their coastal fortresses were truly impregnable against the current inventory of Allied weapons. This psychological barrier was almost as important as the physical one, forcing Allied command to acknowledge that a new, unconventional approach was desperately needed. The existence of the shelters allowed the U-boat fleet to sustain its operations through the worst periods of Allied air superiority, continuously feeding the threat in the Atlantic. The construction of the U-boat pens was an immense logistical and engineering undertaking, driven by the personal urgency of Adolf Hitler. Hitler recognized the U-boat fleet as his primary tool for defeating Britain and saw the pens as essential to their long-term viability in the face of superior Allied air power. Organization Todt, the colossal Nazi civil and military engineering group, was put in charge of planning and executing these monumental concrete projects. The workforce was composed of a mixture of German construction specialists, forced laborers, and prisoners of war from across the occupied territories. The sites operated under conditions of extreme secrecy and relentless pressure to finish the work as quickly as possible. The foundation work alone was staggering, often requiring the draining of large sections of the harbor or the driving of deep piles into the unstable coastal sediment. The walls and ceilings were built using a technique of poured-in-place concrete, which allowed the creation of a monolithic, jointless structure that was inherently strong. Massive wooden or steel forms were erected, and concrete was continuously poured into them, sometimes for days on end, to eliminate weak points. The sheer volume of material needed was immense, requiring the constant transport of millions of tons of aggregate and cement via rail and sea. To increase the roof's resistance to penetration, layers of various materials were sometimes introduced, including sand, gravel, and even a form of concrete rubble known as bunker bed. Crucially, the concrete was heavily reinforced with massive networks of steel rebar, creating a rigid and immensely strong internal lattice. This steel framework was designed not only to hold the structure together, but also to absorb and distribute the massive shockwaves from high explosive bombs. Engineers had calculated that a conventional bomb hitting the roof would create a localized explosion, but the surrounding concrete mass would prevent a catastrophic breach. They deliberately designed the roof structure to be so massive that the energy required to penetrate it exceeded the maximum capacity of any bomb then in the Allied arsenal. The result was a series of vast, rectangular blocks of concrete, seemingly indifferent to the hundreds of tons of high explosives dropped upon them. The base at St. Nazaire, for example, eventually featured a roof up to 8 meters thick in certain sections, built in multiple phases to cope with the escalating Allied bombing threat. The German engineers were immensely proud of their work, viewing the pins as a technical triumph that neutralized the enemy's most significant advantage, air superiority. They believed they had achieved a defensive stalemate, a permanent safe haven from which their U-boats could wage their destructive war. The pins were not merely military installations. They were concrete monuments to the German concept of Festung Europa, or Fortress Europe. Every finished pin provided a sense of smug security to the U-boat crews, who could now rest and prepare for their next voyage with the confidence of absolute safety. The development of the U-boat pins triggered an intense, though initially one-sided, technological arms race in military engineering. The Allied air forces were acutely aware that their bombs were becoming obsolete against the continually thickening concrete roofs. As the war progressed, German engineers responded to every increase in Allied bomb size by adding another meter of reinforced concrete to their coastal bunkers. This created a vicious cycle where Bomber Command's efforts were always lagging behind the defensive construction program of Organization Todt. The standard British high-explosive bombs of the era, though destructive on unfortified targets, simply lacked the kinetic energy and explosive force needed for deep penetration. Even a direct hit from the largest available bombs would merely scrape the surface or cause localized spalling, which the Germans could quickly repair. The German strategy was based on the simple physical principle that the required depth of penetration is directly proportional to the mass of the material to be breached. By continuously increasing the thickness of the overhead concrete, they effectively raised the bar for a successful attack beyond the capacity of current Allied aircraft and ordnance. The sheer mass of the structures also meant that even a massive explosion on the surface would not transmit enough concussive force to harm the U-boats moored far below. Intelligence reports flowing back to London confirmed the devastating effectiveness of the German concrete defenses and the futility of current bombing tactics. Air Chief Marshal Sir Arthur Harris, head of Bomber Command, became increasingly frustrated with the seemingly endless stream of failed missions against these targets. His pilots risked their lives flying through heavy flak only to confirm that the concrete remained uncracked and the U-boats untouched. The cost in aircraft and aircrew was becoming disproportionate to the minimal damage inflicted on the German war machine in its most protected strongholds. The Allies began experimenting with delayed fuse bombs, hoping to achieve penetration through sheer velocity before detonation. But the thick concrete still proved too much. Specialized blockbuster bombs, designed to destroy city blocks with blast rather than penetration, also proved useless against the monolithic concrete pins. It became painfully clear that a fundamentally new weapon was needed, one that completely redefined the concept of aerial bombardment against heavily fortified targets. The solution could not be a marginal increase in current bomb size. It required a conceptual leap in how aerial explosives were designed and deployed. This technological challenge was ultimately entrusted to a single brilliant mind, a man who had already revolutionized the destruction of German dams. The battle had shifted from a test of explosive power to a challenge in applied physics and structural mechanics. The Germans had created a fortress, and the Allies needed to invent a geological event to defeat it. The initial years of attacking the U-boat pens were characterized by a deep and demoralizing cycle of effort and disappointment for the Allied air forces. Mission after mission was launched, involving hundreds of heavy bombers, often traveling vast distances to reach the heavily defended coastal bases. The psychological toll on the bomber crews was significant, as they understood they were flying into the most dangerous airspace for a result that was almost always negligible. The Germans used the U-boat pens as centers for their entire coastal defense network, concentrating anti-aircraft artillery around the structures like a metallic shield. Flak concentrations at bases like Lorient were legendary and terrifying, making the final approach a gauntlet of bursting shells and tracer fire. When the bombs finally fell, the air crews could observe the impacts, but the expected catastrophic explosions simply did not materialize on the concrete roofs. The sight of tons of high explosives exploding harmlessly on the surface reinforced the idea that these German pens were truly indestructible by current means. Target assessment photographs brought back by reconnaissance aircraft told a grim story of superficial damage and rapid German repair work. The intelligence showed that the U-boats were continuing their operations largely unimpeded, resting securely within their concrete caves. This sustained failure posed a significant strategic problem for the Allied war effort, indicating a critical gap in their offensive capabilities. The air campaign was effectively being rendered useless against the most vital German naval infrastructure on the Atlantic coast. Commanders began to question the utility of the missions, weighing the high cost in aircraft and aircrew against the near-zero strategic return. Some tactics were attempted, such as pattern bombing to hit the narrow entry channels when the gates were open, but these were low-percentage shots. The sheer size of the concrete blocks, combined with the multiple layers of protection, meant that lateral attacks or attacks on the walls were also ineffective. The German confidence was not misplaced. Their defensive engineering had temporarily overcome the existing offensive air technology. The only way to truly stop the U-boats was to catch them in the open sea, an operation that was resource-intensive and depended heavily on chance and code breaking. The air offensive against the pens represented a critical moment where conventional wisdom and standard weapons had reached their limit. It forced the Allied scientists and engineers to step away from incremental improvements and pursue a radical, transformative solution. The inability to crack the concrete was a constant, frustrating reminder that the German industrial and military challenge was still profound and adaptable. The airmen waited for a miracle weapon, something that could match the audacity of the German construction with an equally powerful destructive force. The search for a solution to the concrete pins led directly to the brilliant and unconventional mind of British engineer Sir Barnes Wallis. Wallis was already famous for his design of the Wellington bomber and, Most recently, the revolutionary bouncing bomb used in the audacious Dambusters raid. His expertise lay in thinking beyond standard explosives, focusing instead on mechanics, energy transfer, and precision physics. Wallace understood that the problem with the U-boat pins was not a lack of explosive power, but a failure to efficiently transfer that power to the target's critical point. He developed a new theory of bombing based on the concept of maximizing the weapon's destructive potential by focusing on subterranean impact and shock. His new bomb was not intended to explode on the surface, but to be a precision-engineered weapon that could penetrate deep into the earth before detonating. This would create an artificial earthquake, transmitting its explosive energy through the surrounding ground and bedrock rather than dissipating it in the open air. The resulting shockwave would destabilize and crack the massive foundations and structures from below, making the invincible concrete irrelevant. He reasoned that even if the bomb did not penetrate the roof directly, its seismic effect could still undermine the entire massive structure. Wallace calculated that for this effect to be achieved reliably, the bomb had to be significantly larger and heavier than anything then in operational service. This led to the concept of the earthquake bomb, a weapon designed to be a geological force rather than a purely explosive one. The design was characterized by an extremely tough, highly streamlined casing and a very deep penetrating nose, allowing it to survive high-speed impact with concrete or earth. Crucially, the Tallboy incorporated a time-delayed fuse, ensuring the detonation occurred only after the bomb had buried itself deep beneath the target. The sheer size and weight of the proposed weapon posed an immediate challenge to the existing inventory of Allied bomber aircraft. Only the largest four-engine bombers, specifically the Avro Lancaster, would be capable of carrying the new ordnance, and even they required significant modification. Wallace's design was met with initial skepticism, as its sheer scale and unconventional principles were a radical departure from established military doctrine. However, the continued failure against the U-boat pins provided the necessary urgency to approve his revolutionary, yet practical, proposal. The scientific solution was a perfect marriage of physics and engineering, designed to exploit the very mass and rigidity the Germans relied upon for protection. The resulting weapon, named Tallboy, was an engineering marvel and a terrifying expression of scientific warfare. The bomb weighed an astonishing 12,000 pounds, or over 5 tons, a payload unprecedented for a conventional aerial bomb of the era. Its physical dimensions were equally impressive, necessitating major structural modifications to the Avro Lancaster bomber to accommodate its length and girth. The sleek, highly aerodynamic casing was a key feature, designed to ensure the bomb achieved maximum terminal velocity during its long drop. This high speed upon impact was vital for the bomb to drive itself deep into the ground, achieving the necessary subterranean positioning before detonation. The casing was constructed from thick, high-strength alloy steel, engineered to survive the immense shock of penetrating several meters of earth, stone, or even concrete. The explosive payload itself was a powerful mix of RDX and TNT, a potent combination optimized to deliver maximum seismic energy upon explosion. Tallboy represented a conceptual shift from blast damage, which was ineffective against the pins, to structural damage via transmitted shockwaves. The primary target was not the roof itself, but the vulnerable earth and foundations beneath the massive concrete blockhouse. A specialized version of the Lancaster, capable of handling the enormous weight and size, was developed and designated as the BI Special. These modified Lancasters had their mid-upper turrets removed and their bomb bay doors cut away to allow the Tallboy to be carried in a semi-recessed position. The aircrews assigned to the Tallboy missions were highly skilled, requiring exceptional precision to drop the weapon accurately from high altitude. The margin for error was extremely narrow, as the bomb had to strike within a very small area to maximize the seismic effect on the foundations. The Tallboy was ultimately a single-purpose weapon, created almost entirely to solve the specific, intractable problem of the German U-boat pins and similar fortified targets. Its introduction into the Allied arsenal signaled the end of the defensive dominance enjoyed by the German concrete fortresses. The appearance of this massive, new weapon was a closely guarded secret, designed to deliver a decisive psychological and physical shock to the enemy. The Allies were now equipped with the ultimate bunker-busting tool, a weapon that effectively brought the power of a localized earthquake to the battlefield. The first successful deployment of the Tallboy bomb against the seemingly invincible U-boat pins marked a watershed moment in the air war. The missions required perfect weather conditions, exceptional crew coordination, and meticulous precision from the specialized Lancaster squadrons. Operating from high altitude, the crews used the highly accurate, stabilized automatic bomb sight, or SABS, to ensure the Tallboy hit its target with minimal deviation. The initial targets were often the heavily reinforced pins in northern France, which had stubbornly resisted all previous conventional attacks. The approach to the targets remained a significant challenge, with the Germans still operating their formidable flak batteries positioned directly on the bunker roofs. The Tallboys were released from heights often exceeding 18,000 feet, allowing them to gain maximum momentum and velocity during their descent. The characteristic whistling sound of the massive bomb as it fell became a terrifying and unfamiliar sound to the German defenders on the ground. When the Tallboy struck the ground or the roof, it was not followed by the instantaneous explosion of earlier bombs, but a moment of deceptive silence. The heavy, streamlined casing drove the bomb deep into the earth or punched through the concrete before the delayed fuse finally triggered the explosion. The result of the subterranean detonation was exactly as Sir Barnes Wallis had theorized, creating a violent, localized shockwave. The earth around the pens heaved and trembled, and the massive concrete structures, though unpenetrated on the surface, were violently shaken from their foundations. The shockwaves found and exploited the natural structural weaknesses in the massive blocks of concrete and steel. Initial strikes showed that the pins were not immediately obliterated, but were instead critically damaged in a way that was almost impossible to repair quickly. The massive concrete roofs began to spiderweb with fractures, and support columns deep inside the pins were cracked and compromised by the seismic jolt. Water mains burst, dock machinery seized up, and the very stability of the vast, monolithic structures was permanently undermined. The success of the Tallboy was not measured in immediate, visible destruction, but in the structural incapacitation of a previously invulnerable facility. It was a victory of calculated physics over sheer mass, demonstrating that the ultimate defense lay not in thicker concrete, but in a failure to anticipate a completely new type of attack. The most spectacular and strategically significant success of the Tallboy was the moment it finally breached the thickest German concrete. This achievement required both the immense force of the bomb and a degree of luck, often involving a strike on a previously weakened section or a perfect angle of impact. When the Tallboy did penetrate a multi-meter thick roof, the effect was cataclysmic, instantly transforming the inner sanctum of the pen into a death trap. The penetration was achieved not purely by explosion, but by the kinetic energy of the 12,000-pound projectile driving itself through the layers of material. Upon the subterranean or deeply embedded detonation, a massive plug of concrete and steel would be violently ejected or collapsed into the berths below. This resulted in a massive, jagged hole, a gaping wound in the heart of the formerly invincible fortress. The initial breach was often followed by the collapse of surrounding structural elements due to the massive transmitted shock and the removal of supporting material. Inside the pens, the damage was overwhelming, with tons of rubble-crushing equipment, damaging U-boats, and contaminating the docks with concrete dust and debris. The precision engineering of the Tallboy meant that even non-penetrating hits were still debilitating, causing doors to jam and machinery to vibrate off their mounts. The damage was often insidious, with hairline cracks growing into structural failures that forced the Germans to abandon certain sections of the base entirely. At bases like Lorya, repeated Tallboy strikes gradually and systematically neutralized entire blocks of the massive submarine shelter complex. The loss of a single pen meant the loss of berths, maintenance bays, and crucial supply points for the U-boat fleet. The breaches were psychologically devastating for the German crews, who had been promised absolute safety within the concrete walls. The sight of a gaping hole in their supposedly bomb-proof roof was the ultimate sign that their sanctuary had been violated and their mission compromised. The cost of a single Tallboy was immense, but its strategic return in crippling a vital German resource was priceless to the Allied war effort. The period of invulnerability was over, and the very symbol of German defensive arrogance was now shown to be fundamentally flawed and destructible. The success of the Tallboy bomb fundamentally altered the strategic equation of the Battle of the Atlantic in the later stages of the war. The systematic destruction and structural incapacitation of the U-boat pens delivered a crippling blow to the German submarine campaign. Once the pens could no longer guarantee safety, the risk-reward calculation for U-boat operations shifted dramatically against the German Navy. The sustained Tallboy attacks meant that even when a U-boat returned successfully from patrol, it could no longer rely on a secure base for essential repairs and rearmament. Maintenance became a logistical nightmare, forcing the Germans to attempt repairs in less protected, ad hoc berths or to abandon damaged pens entirely. The specialized repair infrastructure, the heavy machinery, and the massive overhead cranes were often rendered unusable by the shock damage and debris. As pens were damaged or abandoned, the concentration of the remaining U-boats increased, making the remaining operational pens even more attractive targets. The psychological impact led to a significant drop in morale among the U-boat crews and the support personnel stationed at the coastal bases. The realization that their supposedly invincible shield could be penetrated or structurally destroyed created an atmosphere of constant fear and vulnerability. The German response was a frantic effort to further thicken the roofs of undamaged pens, but by this point, the war was turning and resources were scarce. The construction of new layers of concrete became a desperate, often futile race against the inevitable return of the Tallboy-equipped Lancaster squadrons. The ability of the Allies to strike deep into the coastal fortresses freed up conventional bomber resources that had previously been tied up in ineffective attacks. The effective neutralization of the U-boat layers helped to finally close the Atlantic gap, securing the vital supply lines between North America and Britain. The fall of the submarine layers was a gradual process of attrition and incapacitation, not a single spectacular victory, but its cumulative effect was decisive. The U-boat threat was never completely eliminated until the very end of the war, but its strategic effectiveness was profoundly diminished by the Tallboy's power. The success of the Tallboy and its larger successor, the 22,000-pound Grand Slam, established a new paradigm for attacking heavily fortified targets. The German U-boat pens, along with other seemingly indestructible targets like V-2 launch sites and viaducts, were finally made vulnerable. The strategic aftermath was not limited to the U-boats, but extended to the entire German defensive infrastructure across the continent. The successful penetration of the massive concrete redefined the limits of what was achievable with air power alone. It proved that no matter how thick or reinforced a structure, a sufficiently large and precisely delivered kinetic weapon could ultimately defeat it. The German military leadership was forced to divert immense resources and manpower away from the front line to attempt to repair and reinforce the damaged coastal bases. This diversion of effort was a strategic victory for the Allies, stretching the already dwindling German industrial and logistical capacity. The U-boat crews were increasingly forced to operate from more distant and less secure bases in Norway or Germany itself, lengthening their transit times and increasing their exposure. The loss of the French Atlantic bases meant that the U-boat war was pushed further out into the open ocean, where Allied air and naval superiority was overwhelming. The Tallboy missions contributed significantly to the ultimate defeat of the U-boat menace, ensuring the successful buildup for the D-Day invasion. Had the U-boat pens remained fully operational and invincible, the logistical challenges of supporting the Normandy landings would have been far greater. The precision and effectiveness of the earthquake bombs ensured that critical military infrastructure could be eliminated with fewer aircraft and fewer missions. It was a clear demonstration of how a single, brilliant technological innovation could completely neutralize years of complex, expensive defensive engineering. The era of the purely passive, monolithic concrete defense was effectively ended by the introduction of this new class of heavy, deep-penetrating bombs. The technology pioneered by Sir Barnes Wallis would continue to influence military ordnance design for decades, proving its revolutionary impact far beyond the Second World War. Today, many of the massive U-boat pens still stand along the French coast, silent, decaying monuments to the ultimate failure of defensive arrogance. Their sheer size is a testament to the engineering ambition of the Third Reich, but their scars are a permanent reminder of the Tallboys' decisive power. The huge, jagged holes punched through the multi-meter-thick concrete roofs remain visible in places like Lorient and Saint-Nazaire. These concrete monoliths survived the war and have proved too difficult and expensive to fully demolish, a lasting symbol of the scale of the original construction. They stand now as a unique type of historical ruin, a massive, block-like structure that survived decades of natural decay and exposure. The pens have since been repurposed in various ways, often serving as industrial storage, yacht moorings, or, ironically, as sites for historical and maritime museums. Visitors can walk among the massive concrete columns and see the evidence of the Allied bombs, the spalling, the cracks, and the indelible impact marks. The legacy of the U-boat pens and the Tallboy bomb is a powerful historical lesson in the relationship between offensive and defensive technology. It demonstrates that no single technological advantage is permanent, and every defense can eventually be countered by a more clever and powerful offense. The story is a tribute to the ingenuity of engineers like Sir Barnes Wallis, who could look at a seemingly impossible problem and find a solution rooted in fundamental scientific principles. The development of the earthquake bomb was a crucial turning point in aerial warfare, creating the precursor for modern bunker busting and precision guided munitions. The very concept of delivering a weapon so large it created a seismic effect was a leap in thinking that permanently changed how strategists viewed fortified targets. The U-boat pins represent the height of defensive military construction, but the Tallboy represents the genius required to overcome such seemingly insurmountable barriers. They stand as a permanent, physical record of one of the greatest technological duels of the Second World War, a duel that the Allies ultimately won by cracking the concrete. The silent, moss-covered bulk of the abandoned pens continues to whisper the story of German confidence and the powerful, heavy reply from the skies above.